Exponential functions. Exponential functions are characterized by variable exponents. So you have, instead of your x being down on the ground like normal, your x is an exponent. And they model situations that exhibit exponential growth, such as a rabbit population doubling every 6 weeks, or exponential decay, such as the half-life of chemical compounds. And the basic form of these functions is f of x equals b to the power of x. If the exponent is positive, such as in y equals 2 to the power of x, then the function is increasing, which is exponential growth. If the exponent is negative, like y equals 2 to the negative x, then the function is decreasing, which is exponential decay. And you can see, for example, in the increasing one, how the increasing happens slowly, and then it picks up speed and shoots up really fast. And that's the nature of exponential functions. Now we're going to graph by making a table. F of x equals 4/3 to the power of x. And so that we all have the same points for our table, let's use -2, -1, 0, 1, and 2. And then you'll fill those in one at a time for x, put it in your calculator, get the y values. Notice in the middle when x is 0, you have 4/3 to the power of 0, which is 1. Any number to the power of 0 equals 1. And you can plot your points and connect, and you should have somewhat of a curve for these graphs. Thing about that. In your table, if you don't want to keep typing the same formula over and over again into your calculator, if you've got the graphing calculator and you push second enter, it will call up the last thing that you typed in, and then you can just edit it and not have to retype the whole thing again. A common use of exponential functions is calculating interest. And here's the formula for compound interest. If you can see the formula buried in there amongst my descriptions of the variables. A equals P times 1 plus R over N to the power of NT. A stands for the accumulated value. That's how much you end up with what you invested and the interest all together. P is the principal. That's the starting amount. R is the rate. It will be given to you. It's an interest rate. It will be given to you as a percent. You need to change it to a decimal. You'll move the decimal 2 places to the left. N is the number of times per year the interest is compounded. So if it's every 6 months, that would be twice a year. If it's weekly, that would be 52 times a year. And that's what the N will be. And then the T is the time in years. So it says $5,000 is deposited into an account paying 9% interest compounded daily. How much will the account be worth in 5 years? So the 5,000 would be the P, that's the amount we're investing, the starting amount. 9% is the interest rate, but we need to change that to a decimal. So we move the decimal 2 places to the left, and it's 0.09. Compounded daily, that would be the N value, and daily would be 365 times a year. And then how much will the account be worth in 5 years? 5 would be the T. So let's fill all that in. A equals 5,000 times 1 plus 0.09 over 365 to the power of 365 times 5. And then you would just put all that in your calculator at once, and so after 5 years now in our account we have $7,841.13. A number that appears in formulas when the exponential growth or decay is happening continuously or nonstop is the number e. This value that's a lot like pi because it's irrational, it's never ending, it's a never ending decimal, it doesn't repeat, it doesn't make any patterns. And one way it can be approximated is the formula 1 plus 1 over x to the power of x, where x goes to infinity. That means the x gets larger and larger and larger. To 12 decimal places, you can see an approximation of e, but of course it keeps on going forever. When e has a positive exponent, you have growth. When e has a negative exponent, you have decay. And so we're going to use that in an interest formula. This is for continuously compounded interest. We have A equals PE to the power of RT. A is the accumulated value, P is the principal or the starting amount, R is the rate, we change the percent to a decimal, and T is the time in years, and then E is the number E. And there is an E on your calculator. It's above the button that says natural log that we'll talk about later, LN, and then there should be a little E above it. If you invest $7,500 in an account paying 5.35% interest compounded continuously, that's the word you want to look for to know that you're using this formula that has the E in it. How much will you have after 12 years? So I filled in the formula. The P was 7,500. 5.35 with the decimal moved over is 0.0535, and the time is 12 years. So here's the formula filled in, and it comes out to be $14,252.08. Population growth and decay also uses exponential functions. So this problem says the growth of the population of the town of Bubbleyville, that's a little shout out to VeggieTales, can be modeled by f of x equals 5 times 1.001 to the power of x, where f of x is in millions and x is the number of years since 1980. So part A says substitute 0 for x, and without using a calculator, find Bubbleyville's population in 1980. So if x is 0, then it's 5 times 1.001 to the power of 0. And I said just a minute ago, anything to the 0 power equals 1. So it's just 5 times 1, which is 5. Now there's not just 5 people in the town. It said that f of x is in millions. So it's 5 million people. Find Bubbleyville's population in 1990. Well, since x is the number of years since 1980, and we're at 1990, that's been 10 years. So x is going to be 10. Filling in our formula then, f with a 10 filled in would be 5 times 1.001 to the power of 10, which comes out to be 5.05. And again, that's million. Predict Bubbleyville's population in 2020. So again, x is the number of years since 1980. If we're at 2020, that's 40 years. So we plug a 40 in for x. 5 times 1.001 to the 40th power comes out to be 5.2, and that's million. Now that prediction would only hold if the population continued to grow at the same rate as it had been in the past. This is a memory retention formula. And so this tells us if we learn something and then we don't look at it anymore, we can plug in how many weeks it's been since we've learned it, and this formula tells us how much is still left in our brain, how much we still remember. And of course, this would just be for an average person. There are people who are better and worse at remembering things. But this is an interesting formula. F of x equals 80 e to the power of negative 0.5x plus 20. Notice the exponent is negative, which is decay because you're forgetting things as time goes on. And x is the number of weeks since the information was received. So the example says find the percent of information remembered after 8 weeks, which is half a semester. So I'm going to fill an 8 in for the x. F of 8 equals 80 e to the power of negative 0.5 times 8. And then a plus 20 at the end, and when you put all that in your calculator, you get 21.5, and that's a percent. So if you learn something at the very beginning of a semester, but you don't ever look at it again, then at midterms, you will have remembered 21.5% of it.